Hi everyone. So this is the second weekly session for the course on river engineering. This course is an NPTEL course with the SWAYAM initiative, and this course will be tutored by Professor Subhashish Datta from the Department of Civil Engineering in IIT Guwahati, and I am Abhishek Chakraborty, a PhD student under the Prime Minister's Research Fellowship scheme in the Interdisciplinary Center for Water Research at IISc Bangalore. Yeah, as I discussed in the last weekly session too, we are going to uh, upload all our videos of the live weekly sessions on our on our YouTube channel, which is titled River Engineering. So far we have already uploaded the assignment zero solutions and the weekly session one there. So this is the URL of that YouTube channel. Apart from that, all the files which are relevant to the sessions which I will be covering will also be uploaded in a Google Drive folder, and this is given here. The links of both the YouTube channel as well as the Google Drive folders are already available in the announcement section of that of this NPTEL course. And I will make sure to upload the files as well as the video recordings as soon as possible, right after the class ends. Yeah, so today we are going to discuss six different very essential questions, which solving which I am pretty sure that assignment number two should be easy after that. But before that, I would like to discuss a few concepts. So I will take a slide more. Yeah, so from the class we learned that the expression of continuity equation, which is very necessary for solving these assignments in three dimension, would look like this in its generalized form: del rho by del t plus del by del x rho u plus del by del y rho v plus del by del z rho w is equal to 0, where the u, v and w are the x, y and z components of velocity respectively. So this is the continuity equation for fluids in three dimensional. Now this is valid for both steady and unsteady flow because it's a generalized expression. Steady as well as unsteady flow. This is also valid for uniform and non-uniform flow. And this is also valid for compressible and incompressible flow. So steady flow means that the parameters are not changing with respect to time. Uniform means it does not change with respect to the direction, and compressible flow means that the uh, density does not change. So let us just take some conditions to this. Number one, what happens for steady flow? So we know that for steady flow, the time derivatives become zero because the time rate changes. There is no change with respect to time. So this first term will become zero. So the expression will be just del by del x of rho u, this is u, plus del by del y of rho v plus del by del z of rho w equal to 0. So this will be the term for only steady flows. Let us take another condition. What happens for incompressible and steady flows? So for incompressible flow, rho will be equal to constant. The density will not change. So we can take out rho from this expression. It will become rho del by del x of u plus rho del by del y of v plus rho del by del W of Z equal to 0, which would give us the very simplified expression del U by del X plus del V by del Y plus del W by del Z equal to 0. So these are the two conditions or cases we can take to simplify the continuity equation in three dimension. However, it's better to uh, recall the generalized expression always before solving any problem. Now so this was the continuity equation for any kind of fluid. Let us see what would happen for in case of an open channel. So now we are proceeding to continuity equation for open channel flow. So from the class we already know that the expression for the continuity equation for open channel flow would look like this: del q by del x, that is the space derivative of the discharge plus the time derivative of the cross sectional area would be equal to the lateral flow into the open channel. So this is known as the conservation form of the continuity equation for open channel, and this small q is lateral flow, and it would be 0 for cases where there is no lateral flow. So this was a conservation form. Let us move to the non-conservation form of the continuity equation for open channel. So non-conservation form would mean that we are finding the same continuity equation along a unit width element. So since it's a unit width, so the area which was actually b times y, or the top width times y, is equal to become y. Since b was equal to 1, its unit width. So let us just put it into this expression. So del by del x of q would be nothing but a times v, and a here is equal to y times v. So this would become y times v plus del by del t of a. A is equal to y equal to q. So let us just use the product rule to fragment the first expression of the left hand side. So this would become v del y by del x plus y del v by del x plus del y by del t is equal to small q, which is the lateral flow. So this is the non-conservation form of the continuity equation for open channels. So we are having q in the right hand side. So let's just see what happens when q is positive and when q is negative. So when q is positive, it will become a losing stream. I will explain it using a diagram too. And when q is negative, it becomes a gaining stream. So let us suppose the cross section of the open channel will look like this. This is the length of it, and this is the cross section. So if there is a inflow of lateral flow into the system, then we call it as gaining stream. Then we call it as gaining stream. Sorry, I have actually reversed the signs. For gaining stream, the q needs to be positive. For losing stream, the q needs to be negative. Okay, so whenever there is a lateral flow or lateral entry of water into the cross section, then we are terming it as gaining stream, and for that q would be positive because it's adding water to the system. And when the opposite happens, when the water comes out of it, then we will term it as a losing stream. So Losing stream will would mean that water moves from stream to sides or to groundwater also. If it's lateral, then it would be to groundwater also. And the opposite happens in a case of the gaining stream. So let us just again write it in terms of write the continuity equation in terms of the top width. Let us suppose top width of channel is equal to T. So the conservation form we remember would be something like this: del Q by del X plus del A by del T is equal to small q. That was the conservation form. Now area we can also represent it as the summation of the top width times the water depth. So Q, or the depth of the flow. And I think someone still. And the discharge would be equal to the cross sectional area times the velocity. So the area would be t times v, t times y, as I had already discussed, times the velocity. So this would be t by v. Let us just again put these expressions into the conservation form of the continuity equation. So we would get del by del x of q. Q happens to be t y v in our case, plus del y del t of A. A will be t times y is equal to small q, which is the lateral flow. Now just assume that the top width is equal to constant. Then we will get another form of the continuity equation, uh, del by del x of yv, taking the constant top width outside, plus del by del t y, taking the constant t again constant, is equal to q. So this would give us, after performing the product rule, this would give us v times del y by del x plus y times del v by del x plus del y by del t is equal to q by t. So this is the final formulation in case the top width is given in our problem. Now the mass conservation is done. Let us just move to the second most important formulation, or the second most fundamental equation in fluid mechanics, that is the momentum conservation equations. So for that we would be utilizing the Euler's or Euler's equation, which is only for inviscid flow, I mean the flows which are not viscous in nature. If that is viscous, then that would become the Navier-Stokes expression. So this is also the momentum equation, momentum conservation. I will be describing the Navier-Stokes formulation also in around 10 minutes from now. So let us suppose we are taking an infinitesimally small control volume which would look like a cube. So this is the infinitesimally small control volume. Let us take another face which is right at the center of this infinitesimally small cube. Uh, we can take our coordinate axis like this: z, x, y, and x. So the dimensions of this infinitesimally small cube would look like this. So this would be a small incremental increase in size, that is dz. This would be dx, and this would be dy. So Very sorry for that. Yeah. So if the pressure happens to be P right at the center face of this elementary cube, infinitesimally small elementary cube, then we would find out that, again, sorry, yeah, again it's right, if it is at the center, so this will become dx by 2, and this will also become dx by 2. So the pressure will differ. It would be compressive because it's hydrostatic one. So the pressure will differ at the two end faces of this dy times dz phase. So the pressure at this phase would be equal to P plus an increment del P by del x, because the pressure change along the dx direction, just multiply it by the length traversed by it, that is dx by 2, because it was right at the center, and then multiply this pressure into the face area just to convert this pressure into the force. The face area we can see is dx times dy. So sorry, dy times dz. Again, the pressure here would look like P, which was the center pressure, minus del P by del Z. Why minus? Because the center was assumed as the origin. Del P by del X into dx by 2, because it is dx by 2 distance away, into dy by dz, just to convert the pressure into force. So here P is equal to pressure intensity at center of the element, and we will be describing something known as Gx later for the Euler's equation. Gx would be the body force per unit mass in x direction. So just combining it, we can write the net force in the x direction to be P minus del P by del x times dx by 2, into just converting this pressure into force by multiplying it by area. This is just this expression, minus, why minus? Because it is acting at an opposite direction, it's towards the body, plus del p by del x times dx by 2 into dy dz. Again we are just converting the pressure into force, plus the body force. Body forces are the forces which act entirely along the volume of the control volume, and in our case the very prominent body force happens to be that of the gravity or the weight. So just multiply it with the mass dx dy dz. So Gx is a body force per unit mass, and we are multiplying body force per unit mass into mass. So this is rho times rho times the volume. To convert rho times the volume would be nothing but the mass. So Gx times the mass would be equal to the force, and this would be equal to the change, plus Gx times rho times dx dy dz. So this is the expression we find from it. Let us take another slide. We just need to use the second law of Newton, that is the net force would be nothing but the mass times acceleration. So we just put rho dx dy dz for volume and ax to get the final expression for the Euler's equation for conservation of momentum. So the final expression would look somewhat like this: u del u by del x plus v del u by del y plus w del u by del z plus del u by del t is equal to minus 1 by rho del P, that is a pressure intensity P, plus Gx. Gx is the body force. So this is the Euler's expression in the x direction. That is why all the velocity components are u here. Let us similarly write the y Euler's expression in the y direction and the Euler's expression in the z direction. So similarly, the those expressions would look like this: u times del v by del x. It's very easy. Just substitute u with v. That is the x component velocity with that of the y component velocity to get the y direction Euler's expression, plus v times del v by del y plus w times del v by del z plus del v by del t is equal to minus 1 by rho del p by del y, because it's of y direction, plus gy, that is the body force along the y direction. And similarly we can also write it for the z direction very in a very similar sense. Just substitute v with w and y with z. So it would look like this. Is equal to minus del p by del z, because we are finding it for the z direction, plus g of z, that is the body force in the z direction. So something to be very something which is very interesting and important in this is that the first three expressions on the left hand side, this would be known as convective acceleration. Convective acceleration in u direction, and this term del u by del t is known as the local acceleration. So overall this left hand side would be nothing but the acceleration part of the Euler's equation, and right hand side would be equal to the force related part of the Euler's equation. The first the first uh, expression the first expression on the right hand side would be equal to the net force due to pressure variation in x direction. Net force due to pressure variation, and the second one is force due to gravity, which is a body force in our case. Force due to gravity in x direction. So far we are done with the continuity equation, which is nothing but the conservation of mass, and the momentum equation, which is the Euler's equation. Before moving to the first question, I would give some expressions to understand what are the correction factors. So let us just see how the velocity distribution would look like in an open channel flow. Velocity distribution in open channel flow. So let us suppose this is the stream, the top view of the stream, top view, or also known as plan in civil engineering terms. So the velocity distribution would look somewhat like this. The highest velocity, the largest velocity will be right at the center of the stream. That is equidistant from both the banks. The velocity distribution would look like this. Largest velocities at the center of the stream, that because the boundary effects would be minimized. So this is the top view or the plan, and these two are the stream banks. Now what about the velocity distribution with respect to the depth of the flow? So let us suppose this is the surface, this is the free surface level or the water depth. Let us suppose the water depth is something like this. Y naught is the water depth. So velocity distribution looks somewhat like this. This is the surface. This is the surface. So right before the surface, the velocity decreases. So one thing is to be assured is that this is non-uniform. This is not constant. The velocity distribution is not constant with respect to the depths. The top velocity may be the velocity of the surface, and the velocity right at the bottom would be zero because of boundary effects. And this velocity distribution may be described by logarithmic or exponential expressions, by logarithmic or exponential, that is power law distribution. Please feel free to ask me questions if there are any in between. You can just unmute yourself and ask your questions. So the funda is that the velocity is zero at boundaries and it gradually increases with increasing distance from the boundary. Again, what we would expect is that the highest velocity should happen at the free surface level or the water surface, but that doesn't happen. You can see that the velocity suddenly decreases. The velocity suddenly decreases. So the maximum velocity of flow occurs at a certain distance below the free surface. Free surface is the one in which the shear stress is zero. Okay, so this reduction is basically due to several factors. Some of them are: number one, production of secondary current, which is the function of aspect ratio, that is B by Y. Also, some studies also attributed to the wind stress at the top of the surface, due to which the velocity suddenly decreases. Now let us just see how the velocity distribution would look like, or the highest maximum point of maximum velocity would look like for a very narrow channel versus a very wide channel. Yeah, before that, this point is the one in which there is the velocity is the maximum. So this is the V max point. Now let us just compare how the velocities would look like for a wider channel versus a narrow channel. Wider channel versus narrow channel. So for wider channel, the aspect ratio, or B by Y, that is the ratio of the width to the depth of the flow, would be much larger than 5 usually, and for narrow channel the ratio would be less than 5. So let us just see how it would look like. Let us just suppose we are taking a case in which uh, the depth of the flow is same for a narrow versus wider channel. So the depth is same. Depth here is also y, and here it is also y. However, the width is highly different. It is b1 here and b2 here in the narrow channel, and b1 is much larger than b2. That is to be noted. So the v max, that is the point of maximum velocity, will also differ. The point of maximum velocity will be downward, from the much downward from the surface of the water in case of narrow channel than that of wider channel. So that is something which we need to also understand. So before moving into the first question, I will give use. I will explain one last concept about the velocity and the average velocity and the kinetic energy and momentum correction factors, because such questions have been asked in the assignment too. So, what is the average velocity of a channel? Average velocity of channel. What is it actually? So we have seen that the velocity changes a lot. It would look somewhat like this. So this velocity changes a lot. It is zero at the bottom, V is equal to 0, and it is maximum somewhat below the surface of the water. So this is, it is like this. Now the average velocity can also be found out by just multiplying the discharge. I mean, just integrating the discharge, that is the velocity at different sections times the incremental area dA, and just dividing it by the total area of the cross section. So this is the expression used for the average velocity, where v is equal to small v equal to actual velocity, and capital V is equal to average velocity. I will explain it using some formulations too. So we know that, let us suppose Q is equal to constant, that is the continuity is maintained, the discharge is not changing across the channel. So V, that is the average velocity, can be written as 1 by A integration over the area V times dA. This implies the discharge would be A times V, capital V here. Capital V would mean the average velocity, and this would be V times d. So this is the expression for the discharge using the average velocity. So let us just move into two very important components: the kinetic energy correction factor and the momentum correction factor. The first one is kinetic energy correction factor, and let us denote it as alpha. So we know that I'm again making the same diagram. The velocity distribution uh, from the bottom to the water surface would look somewhat like this. Just a definition of the kinetic energy correction factor is kinetic energy per time or per second in our case, when we use actual velocity in the expression, by kinetic energy per second when we use the average velocity in the expression. So this would be nothing but kinetic energy expression. So the kinetic energy expression is half mv square. So half mv actual square, because the numerator is by using the actual velocity, by t, because it is the kinetic energy per time, by half mv average square by t. Let us firstly look at the numerator. The numerator states that it is equal to half mv actual square by t. So we can write it as half mass can be written as density times volume into v actual square by t, and volume by t will become nothing but the discharge. So this would be equal to half rho q times v actual square. Now discharge is equal to area times the velocity, which is equal to the actual speed, the actual velocity times the incremental area, and it is integrated over the entire surface. Someone is trying to enter. So capital V in our case is the average velocity, small v is the actual velocity. So we can again write this expression as half rho, just write the q as equal to integration of v times dA. So this would become v actual times dA times v actual square. So finally the numerator would look like this: rho times v actual q times dA. This is the numerator. Now let us come to the denominator. Denominator is nothing but half mv average square by t. we write the mass as equal to density times volume into V average square by T, and volume by time is nothing but the discharge. So this will become half rho Q into V average whole square. I'll take another slide just to explain it. So denominator so far was equal to half rho Q V average whole square. We also know that the discharge can be written as total cross section area times the average velocity, where V is equal to V average. So we can again write this expression as half rho Q can be written as A times V average times V average square. So this would be nothing but half rho A V average whole cube. So alpha, which was the kinetic energy correction factor, which I explained was equal to the kinetic energy per time, considering the actual velocity divided by the kinetic energy per time considering the average velocity, would finally look like this: half rho integral V average cube times d, okay, dA by half rho A V average cube. So we will just this is V actual. So we will just use this expression and just change the notation. V actual can be written as V and V average can be written as capital V. So alpha would finally look like small v times dA, V cube times dA into capital V by capital V cube times A. Capital V is the average velocity and small v is the actual velocity. So this is the expression for kinetic energy correction factor. There is another term known as the momentum correction factor, and the question for that has been asked in the assignment also. I will very quickly finish that. Momentum correction factor beta. So beta is nothing but momentum per time. In our case, we can write as second with respect to the actual velocity by momentum per time with respect to the average velocity. So let us just write the expressions for momentum. Momentum is nothing but mass times velocity. So this is V actual by T by M of V average by T. Let us just look at the numerator first. Numerator is mv actual by T, and M can be written as density times the volume, and V by T will be again written as the discharge. Now Q is equal to AV is equal to, here capital V is the average velocity, is can also be written as the integral the actual velocity times the elementary area. So this expression from this will become equal to, by taking the density outside, it will be V average dA times V actual dA again V actual. So is equal to, this is equal to rho V actual times V actual will become V actual square. So this is the numerator. Denominator again it is equal to mv average by T is equal to mass can be written as density times the volume times V average by T. The volume by T will become the discharge is equal to rho Q V average. So Q will be nothing but A times V from this expression. So we can write it as rho AV times V average can also be written as capital V. Just remember the notations which I just used. So this would be equal to rho A V square. So now we know the terms. If we write V actual is equal to V and V average is equal to capital V, then we can get finally, we will finally get, just dividing the numerator by the denominator, we will get the momentum correction factor as V square dA by V square A. So this is the momentum correction factor. Generally, the kinetic energy correction factor is larger than the momentum correction factor, and they both are larger than 1. For uniform velocity distribution, alpha is equal to beta equal to 1. Why? Because that velocity distribution is same throughout the depth. So that is why there is no difference between the actual velocity and the average velocity. So that is the term for the uniform velocity. Now we can straight away proceed to the expressions, final expressions. So derive the expressions. We can straight away proceed to the questions. So the first question was derive the expressions for the kinetic energy correction factor and momentum correction factor for an open channel. So this we just derived. I will just finally write the expression. Uh, the kinetic energy correction factor. This is right in the last slides. Alpha is equal to the kinetic energy correction factor. Is nothing but the expression was V cube dA by V cube, capital V cube A, where capital V is the average velocity and small v is the actual velocity. Similarly, beta is equal to momentum correction factor. The derivation I just showed in the last few slides would be nothing but integral actual velocity, that is small v square dA by v square A. Refer to last few slides for derivation. So these are the kinetic energy correction factor and the momentum correction factors. Now we will solve a numerical based on these expressions. And a very similar question has been asked in the assignment number 2 also. So this question is, in a circular pipe, the velocity profile is given as u is equal to capital Um times 1 minus r by r square, and where um is the velocity at the pipe axis and r is the radius of pipe. Find number 1 the average velocity and number 2 the momentum correction factor. So the diagram which was given for pipes. So for pipe, it would look like this. This is the pipe surface. This is also the pipe surface. The velocity distribution would look somewhat like this. This would be maximum at the center of the pipe. That is because the boundary effects are the minimum there. So um is the velocity at the pipe axis. It would be max. It would be this because it is the pipe axis. This is the pipe axis. Let us suppose, so okay, so this to this is the total radius of the pipe. Let us suppose we are taking small r, that is the radius from the pipe axis to somewhere in between, and we take an elementary strip for that. So this would be corresponding to, let us suppose, the velocity small u. So the expression looks like this. Let us suppose this is an incremental width dr. So let us suppose we are just taking the cross section of the same pipe which was present in a longitudinal section so far. The cross section would look somewhat like this. We will just extend it. It is a circular pipe. This is the center of the pipe. U, small u is right here, so we can take an elementary strip. The elementary strip would look somewhat like this. Let us suppose the distance or the radius from the center to that of the elementary strip is capital R, and it is capital R, sorry, small r, and it is capital R to the end of the pipe. Let us suppose the thickness of the elemental strip is dr. The thickness of the elemental strip is dr. This is the cross section. So we can write the yeah. So the question is that first of all they want the average velocity. So for the average velocity, we need to first of all find the discharge. So for discharge, we need the area. So the area can be written as the length of the strip, which will be nothing but the circumference times dr. Why? Okay, I will explain why. If you cut this strip and then make it cut this strip and then make it like this, the total length of the strip would be nothing but the circumference of the circle, that is 2 pi r, and we can just multiply the circumference, that is the length, times the thickness of the strip to find out the total area of the strip. So this is 2 pi r, that is the length of the strip, times dr, that is the thickness of the strip. Now this was the elementary area. Now the elementary discharge can be elemental area times the local velocity. So this is 2 pi r dr, just that is just the dA, times velocity. The velocity can written as u. Total flow is equal to capital. Let us just express it using capital Q. Can be do 2 pi r u dr, that is the dq, integrating it over the radius from 0 to r. So this would be 0 to r, 2 pi u, small u can be written as um from the question, times 1 minus r square by r square times r dr. So this would be 2 pi um 0 to r. Just multiply this term into the terms on inside the bracket, r minus r cube by r square dr, which is 2 pi um times, just integrate this term, r will be integrated to r square minus r square by 2, and r cube by r square will be integrated to r power 4 by 4 r square. 0 to r are the limits. So just to end this question, we will finally integrate it. So this will be 2 pi um r square by 2. Just putting the values, the limits to the integration, it would look finally like this. 2 pi um r square by 4 would be the q, the discharge. Now the first question is about the average velocity. Let us suppose it's u bar. So Q can be written as the total area, the cross section area, times the average velocity, which is equal to pi r square, the total area, cross section area, times the average velocity. So just equate these two terms. Pi r square times the average velocity is nothing but the discharge expression which we found out just now. 2 pi um r square by 4. This will give us u is nothing but um by 2. That is the average velocity for a pipe flow is nothing but half times the average velocity for the axis. So that is the final uh, interpretation of this answer. Now moving on, we need to find out the momentum correction factor also. That was the second question. Yeah, we also need to find out the momentum correction factor. It would look like this. momentum correction factor or beta. Beta would look like beta would be nothing but just recalling the expression momentum per second with respect to the actual velocity by momentum per second with respect to the average velocity. So the expression which we derived was like this, where small u is the actual velocity and small u bar is the average velocity. So just putting the expression a times u bar square, just integrate it from 0 to r. So u, capital U can written as, according to the question, um times 1 minus r by r whole square, and just since u is present in terms of since small u is small u is to be squared, we just square it again, multiplied by dA is 2 pi r dr. So just take out the constants. 2 pi is constant, is again a constant, by a u bar square, integrate. So this is to be first of all expressed. So this would look like, this is nothing but a minus b whole square expression. So we can just write it like this: a square minus 2ab minus 2ab plus b square, that is r square by r whole square squares, that is r power 4 by r power 4. So just write the same expression again, by a u bar square, and now we need to integrate it. So this will be r minus 2 r cube by 3 r square plus r to the power 5 by 5 r4 from 0 to r. You just solve this expression. Finally, you will get the value as uh, 2 pi square by a u bar square times r square by 6. So this implies, now a is again, now a, which was essential in this expression of momentum correction factor, would be pi r square, and u bar is equal to by 2, which we just found out from the first question. So this implies beta would be 2 pi square by pi r square times by 2, just multiplied by r square by 6. So beta would come out to be 1.33 or 4 by 3. So this question is also solved. Let us just move to the next question. In a pipe of 100 mm diameter, water is flowing with a mean velocity of 4 meter per second and at a gauge pressure of 400 kilonewton per meter square. Determine the total head in meters uh, if the pipe is 10 meters above the datum line. Neglect friction. Okay, so it's a very straightforward question. Let us suppose this is a pipe and this is the datum. So the the question tells us that the pipe is 10 meters above the datum line. It is 10 meters above the datum line. So we need to find out the total head. The total head expression is very simple. Just recall what we learned from our fluid mechanics class. It is nothing but the datum head plus the velocity head plus the pressure head. So the datum head we know is 10 because it is 10 meters above the datum, plus the velocity, just substitute the value of velocity. G is equal to 9.81 plus pressure is 400 kilonewton per meter square, 400 into 10 to the power 3 newton per meter square, by density is 1000 and G is again 9.81. So the final value of the total head will come out to be 51.59 meters. So overall, this question was relatively easy. Now moving to the next question. In a fluid flow, velocity, field and density variations are respectively defined as V v arrow, that is the vector v vector is equal to 5x I cap minus 30 j cap, and rho, that is the density, is 10x. What value of x does satisfy the continuity equation? So it's again a very straightforward question. We need to just substitute these values into the continuity expression, and then we can find out the value of x. So v is, we will solve it now, 5x I cap minus 30 j cap, and rho is equal to 10x. So first of all, it is a steady state equation, because rho is not given in terms of t. So del by del x of rho u plus del by del y of rho v is equal to 0. There was another term of del rho by del t, but we can just take it as 0 because rho is not expressed in terms of time. Okay, so this, the first term is del by del x of rho. Rho is 10x and u component is 5x, plus del by del y of rho. Rho is 10x and v component of the velocity is minus 30, equal to 0. So this will become equal to 50x square, and the derivative of 50, this will be 50x square, and this would be equal to minus 300x. So 100x plus 0 is equal to 0. So this gives x equal to 0. Expression. Now the next question: in a one-dimensional open channel flow, the discharge Q uh, is defined as 6x square meter cube per second, and area of flow A is equal to 9t square x meter square. Find out the lateral flow at x equal to 50 meter and t equal to 100 seconds. So Q is given as 6x square meter cube per second, and A is given as 9t square x meter square. We remember that the continuity equation, the conservation form looked like this: del q by del x plus del a by del t is equal to small q, that is q is the lateral flow. So del by del x, q is 6x square plus del by del t, a is 9t square x is equal to q. So just uh, differentiate it partially. So 6x square would be 12x plus 9t square would look like 18tx. Just substitute the values given here: x equal to 50 meter and t is equal to 100 seconds. So this would finally come out to be 90,600 meters square per second for t. That is the lateral. So the lateral flow is found out like this. So coming to the last question of this weekly session 2, consider a steady two-dimensional incompressible velocity field with u equal to x minus 4y and v equal to minus y minus 4x. Calculate the pressure as a function of x and y. Assume the gravity components as 0. Okay. So before that, I will just finally give the expression for. Let us just recall the expression for the Navier-Stokes equation. It looked somewhat like this: u del u by del x plus v. Let us suppose we are just considering the x component of the Navier-Stokes equation, plus w del u by del z plus del u by del t equal to gx minus 1 by rho del p by del x. P is the pressure intensity, plus kinematic velocity times Laplacian of u plus kinematic velocity times v into del by del x del u by del x plus del u by del y plus del u by del z. Okay, just one thing is to be ensured is that so far I have already explained the meanings of the terms till this. This was already what we already observed in the Euler's equation. We observe some two distinct expressions added to the Euler's equation to make the Navier-Stokes expression, and this will make the momentum equation to be applicable for viscous flows also. Just recall that Euler's equation was only valid for inviscid flow. When we add the expressions, the two on the right hand side, the two expressions on the right hand side, it will become a very generalized expression known as the Navier-Stokes equation, and it would be applicable for different viscosities also. So it introduces the viscous terms, Navier-Stokes expression. Just a brief recall: the kinematic viscosity nu is equal to the dynamic viscosity times the by the density. So these terms are for the viscous effect, and these are only there in the Navier-Stokes expression. Now coming to the question, consider a steady two-dimensional incompressible velocity flow with uh, u is equal to x minus 4y and v is equal to minus y minus 4x. So we need to find out pressure as a function of x and y, and assuming that the gravity components are 0, gx and gy equal to 0. Let's move to the next slide to understand it. Okay, so u is x minus 4y and v is equal to minus y minus 4x. The first step to any such problem is first of all checking whether these actually these even make sense or not. Check whether uh, continuity equation is applicable. So any fluid should always pass the continuity uh, equation test. So the continuity equation was rho u by, okay, del u by del x plus del v by del y equal to 0. So del u by del x in our term, del u by del x is 1 and del v by del y is minus 1. So it is 0. So continuity equation is applicable. Now we move to the actual question. Step 2 will be using the Navier-Stokes expression. So the Navier-Stokes expression, we just need to substitute it into the Navier-Stokes equation to finally get the pressure term with respect to x as well as y. So let us suppose we write the Navier-Stokes expression in the y direction. So it would look somewhat like this: del v by del t plus u del v by del x plus v del v by del y is equal to minus del p by del y plus rho gy plus mu del 2 u by del x square plus del 2 u, sorry, del 2 v by del x square into del 2 v by del y square. Okay, so first of all, there are two things: the body force component is to be neglected, so it is 0. Then secondly, it is a steady flow, so this will again be 0. So we are left only with this. In case you are wondering how this expression appeared, it is very simple to understand. In the last slide, we just need to substitute the kinematic velocity with the kinematic viscosity with the dynamic viscosity. We will get this expression. So this is because of steady flow, which is given in the problem. Steady flow given in the problem, and gy is equal to 0 because the body forces are been have been asked to be neglected in this question. So just solve this equation, we get minus del p by del y from the right hand side can be written as rho times u u is x minus 4y times del v by del x, that is minus 4, plus v minus y minus 4x times del v by del y, that is minus 1. So this implies del p by del y will finally come out to be minus 17 rho y from the what do we say, the from the y direction Navier-Stokes expression. Similarly, we also need to move towards the x direction Navier-Stokes expression. Let us take this expression as 1. Now x component, x direction Navier-Stokes equation, we need to write rho del u by del t plus u del u by del x plus v del u by del y equal to minus del p by del x plus rho gx plus mu del 2 u by del x square plus del 2 u by del y square. This is Laplacian, plus del 2 u by del z square. This term is to be neglected because there are no second order terms in the u. This is again 0 because it's a steady flow. This is again 0 because the body forces have been asked to be neglected. So this will leave minus del p by del x in the right hand side to be equal to rho x minus 4y times del u by del x. Del u by del x is 1 plus minus y minus 4x, that is the v, times del u by del y, which is minus 4. This leaves minus del p by del x is equal to rho times 17x. So del p by del x is nothing but minus 17 rho x. This is the second expression. Okay, so from the first expression we got del p by del y equal to minus 17 rho y, and from the second expression we finally got del p by del x equal to minus 17 rho x. So how do we find the final expression for p in terms of x and y? Just partially integrate equation 2 with respect to y. Partially integrate 2 with respect to y. So we get p in terms of x and y is equal to minus 17. We would firstly do it with 1 so that the expression becomes a bit more easier. So del p by del y was equal to minus 17 rho y. So it will be minus 17 rho y square by 2 plus an expression of x because it was partial integration. So this will be expression number 3. Now we just need to differentiate it again, differentiate this expression again. So differentiate 3 with respect to x partially. So it will give del p by del x equal to g dash x because there was no expression related to y. So it will just leave g dash x, which we know from equation number 2 is equal to minus 17 rho x. So this would be the expression 4. We just need to integrate it to get the final expression. Gx would look like minus 17 rho x square by 2 plus any constant c1. So this is the expression number 5. So just substitute 5 in equation 3. So we will finally get the expression for pressure in terms of x and y both. So it was minus 17 rho y square by 2 minus 17 rho x square by 2 plus any numerical constant c1. So this would be the final expression for the pressure in terms of x and y both together. So we are done with all the questions. Are there any doubts?
Right, no?
Sorry.
20. So just go to the previous slide, 22.
Sure. Yeah.
First year, first you have partially integrated with respect to y, no? Equation number one.
Yes.
No, no. Before that, actually, that dou p by dou y and dou p by dou x. Can you just explain once more, like?
Okay, so firstly, the answer is like this. Firstly, we will just need to check whether it's a fluid or not. So for that, we need to satisfy the conditions of a continuity equation. So that was del v by del x plus del v by del y equal to 0, and we are finding that it is actually 0. So it is first of all a fluid. Secondly, we need to check whether the Navier-Stokes expression satisfies or not. So we are just putting it into the Navier-Stokes expression. So firstly, I am writing the Navier-Stokes expression in the y direction. This would look like this, right? So since the question states that it is a steady state, asks us to assume that it's steady state. So del v by del t will be 0, and it also asks us to assume that the body forces will be 0. So this will also gy will also become 0, right? So it leaves us with minus del p by del y, which was in the right hand side. We just take it into the left hand side in this expression, and the other terms del 2v by del x square will anyways be 0 because v does not contain any second order expression. So del 2v by del x square will be anyways 0. Okay, so if we bring this minus del p by del y into the from the left hand side, right hand side into the right hand side, we just flip the directions. Okay, now rho into u is x minus 4y, and del v by del x is nothing but minus 4 minus into multiplied by minus 4
Is
plus
it -4 or 1?
minus 4. It is del v by del x.
Okay. Okay, got it, got it.
It is u times del u by del x plus v times del v by del y. Okay. Similarly, we are just doing the same thing for the x direction Navier-Stokes equation also. So we finally find del p by del x is equal to rho times 17x. Okay. So del p by del x can be presented as minus 17 times rho x. Now we know del p by del x as well as del p by del y. We need to find out del p by p of x comma y somehow. So firstly, we just indicate the first expression with respect to y. We will get this thing. Gx will be the function with respect to x, and for finding gx, we again differentiate it. So this would be del p by del x equal to g dash x from this expression, and g dash x will be nothing but the would be equated to equation 2 again. So it would be minus 17 rho x. We just finally integrated to find gx is equal to minus 17 rho x square by 2 plus the any constant c1. Finally, we can write p of x comma y equal to minus 17 rho x y square by 2 minus 17 rho x square by 2 plus c1. Okay.
Yeah, got it, sir.
This question is very similar to the one which is discussed in assignment number 2.
Yeah, it's the last question in the assignment.
Yeah, yeah, exactly, exactly. They have put some. I mean, they are expressing it using some constants a and b. I think in that question. So
Yes.
this would help you solve that question. Then the other questions are very general in the assignments. So one of the question asks you to solve the lateral flow.
Lateral
So
flow.
that you can find out using the conservation or the non conservation form of the mass balance or the continuity expression. And apart from that, all the questions are pretty relatively easy. Any other doubt?
No, sir.
Okay, okay. So I think we are done for the day. Uh,
Yeah, thank you, sir.
Thanks a lot for joining.